The holographic principle is a bold idea in theoretical physics, suggesting that all the information contained in a three-dimensional region of space can be fully described by data encoded on a two-dimensional surface surrounding it. In other words, the true description of reality might live on a flat boundary, and the 3D world we experience could be a kind of projection, much like a hologram appears three-dimensional but is stored on a flat film. And this concept first emerged from studies of black holes. According to Stephen Hawking and Jacob Bekenstein, the maximum amount of information, or entropy, that can fit inside a black hole is proportional not to its volume, but to the area of its event horizon. Why would that be? Imagine cramming more and more matter into a region of space. Eventually, you'd create a black hole. The strange part is that the information capacity, how much detail you could in principle store inside, grows with the surface area of the boundary, not the volume inside it. This defies our everyday intuition, where bigger rooms can hold more stuff. In physics terms, it hints that the universe's fundamental degrees of freedom may scale with area, suggesting a holographic-like storage of reality. Could this principle apply beyond black holes, maybe even to the whole universe? Some theories inspired by string theory propose that the entire cosmos could be described by data on a distant 2D cosmic boundary. If so, our 3D reality might be like a vast, richly detailed projection. This doesn't mean we're living in an illusion, but it does suggest that the underlying mathematics of reality could be fundamentally lower dimensional. Now, here's a curious question. Could such a principle affect how we think about biological systems or information storage in nature? If the universe is holographic at a deep level, perhaps the information needed to describe complex structures from galaxies to living cells could, in theory, be represented with fewer dimensions than we expect. Some speculative thinkers have even wondered if biological surfaces like membranes could encode more than just chemical boundaries, holding complex spatial information in a lower dimensional form. While this remains far outside tested science, it sparks intriguing parallels. The holographic principle hasn't yet been proven for our universe, but experiments in high-energy physics and condensed matter are probing related ideas. Even if it turns out not to be a literal truth, it forces us to reconsider the nature of space, information, and reality itself. If the 3D world is in some deep sense written on a 2D surface, then the fundamental nature of existence might be stranger and more elegant than our senses suggest. The holographic principle arose from studies of black hole thermodynamics, particularly the work of Jacob Bekenstein and Stephen Hawking, who discovered that the entropy of a black hole is proportional not to its volume, but to the area of its event horizon. This suggested that all the information describing the contents of a region might be encoded on its boundary. And Gerard Houft and Leonard Susskind expanded this into a broader principle for the universe. It implies a surprising connection between three-dimensional space and two-dimensional information storage. A black hole's entropy scales with its surface area, not volume, and it's like finding that the contents of a book could be fully described by words printed on its cover. In physics, information refers to the number of distinct states a system can be in, not just words or images, and the holographic principle treats this as a measurable property tied to the geometry of space. If the maximum information inside a volume is proportional to its surface area, reality may be fundamentally two-dimensional at the deepest level, changing how we think about locality, causality, and physical storage limits. It also hints that our three-dimensional perception might be emergent, not fundamental. The Bekenstein bound sets a maximum information limit for any finite region, and it's like discovering your computer's memory capacity is determined by the size of the case, not the number of internal chips. Black holes act as natural laboratories for the holographic principle because their physics tightly links geometry, entropy, and quantum theory. If matter falls into a black hole, the event horizon grows to account for the new information. avoiding paradoxes like information loss since the surface encodes what was inside. Such behavior suggests that any region of space could be described similarly by its boundary data, making black holes prototypes for holographic encoding. Hawking radiation theoretically carries information away from a black hole surface, and a black hole is like a locked safe that shows a changing pattern on its surface whenever something is put inside. In theoretical physics, the holographic principle found strong support in the AD-S/CFT correspondence proposed by Juan Maldacena, which states that a gravity theory in a curved 3D space, AD-S can be exactly equivalent to a quantum field theory without gravity on its 2D boundary. This gave a concrete mathematical realization of the holographic idea, and although our universe is not ADS, the correspondence provides deep insights into quantum gravity and is now a major research tool in high-energy theoretical physics. A 3D gravitational system in AD space can be described by a 2D conformal field theory, and ADS/CFT is like finding two very different languages that tell exactly the same story in perfect translation. If the holographic principle applies broadly, our familiar 3D world might be an emergent phenomenon from 2D fundamental physics, challenging our intuitive sense of space and dimensionality. The real description could be simpler, existing on a cosmic boundary we cannot directly observe, with the 3D space we move through being akin to a projection, like a hologram. This idea is compatible with certain approaches to quantum gravity and space-time emergence. In a hologram, the full 3D image comes from a 2D surface pattern, and reality might be like a video game where the code exists in 2 dimensions, but players experience a 3-dimensional world. The holographic principle implies that the maximum information that can fit inside a region is finite and set by its surface area in Planck units, challenging classical expectations that smaller and smaller regions could store unlimited information. For physical systems, it sets ultimate bounds on computation, data storage, and measurement resolution, limits far beyond current technology but significant for theory, and also offers clues for unifying quantum mechanics and gravity. A cube with sides 1 meter long has an information limit based on the area of its faces, not its volume, and it's like finding that the capacity of a warehouse depends on the size of its doors, not the space inside. Testing the holographic principle directly is challenging because its effects become significant only near the Planck scale, but some experiments search for holographic noise, tiny fluctuations in spacetime geometry that could reveal its discrete structure. Laser interferometers and precision detectors might one day detect such signals, and indirect evidence might also come from patterns in cosmic background radiation or black hole observations. For now, the principle remains mostly theoretical, but inspires creative experiments. The Fermilab holometer searched for holographic noise in spacetime, and detecting holographic effects is like trying to see the grain of a photograph by looking at a mural from across the street. The holographic principle forces us to reconsider the meaning of space and reality. If all the information about a 3D volume resides on a 2D surface, then the inside is just a representation, blurring the distinction between reality and information about reality. This raises questions about whether the universe is a kind of simulation or computation, bridging physics, philosophy, and even metaphysics. Some interpretations liken the universe to a vast informational network. And it's like realizing your favorite landscape painting is made of pixels that encode every detail without actually containing any hills or rivers. Beyond black holes, the holographic principle connects to condensed matter physics, quantum information theory, and cosmology. In some materials, boundary phenomena encode bulk properties in ways reminiscent of holography, and quantum error correction codes mirror holographic ideas by showing how redundancy preserves information. These interdisciplinary links suggest holography might be a universal organizing principle in physics, helping solve puzzles about space-time, entropy, and the quantum structure of reality. Topological insulators have surface states that determine bulk behavior, And it's like judging the quality of a cake solely from its frosting. When finding the frosting contains the entire recipe,